Okay. So we started discussing Riemann-Roch theorem. So this is Riemann-Roch. Okay. So I write again the statement of the theorem. So let x. So basically, it says the following. Let x be a compact Riemann surface, and D a divisor on X, then the formula holds L of D minus L of K minus D is equal to degree of D minus G plus 1. Okay? So this is the formula where, so let's see, L of D is dimension of the space capital L of D, right? Which is the space of all meromorphic forms on X, sorry, meromorphic functions on X, such that divisor of F plus D is bigger than or equal to 0, right? So that's the definition. Okay, so this is dimension over C. Now, what is K? K is a what did we call it? Canonical divisor is any canonical divisor so i.e. So do you remember what is a canonical divisor?
The subset of the principal divisors?
What's that?
It's a subset of the principal divisors.
It's not a subset. It's a divisor. So
A canonical divisor is also a principal divisor.
What's that?
A canonical divisor is also a principal divisor, but the converse is not true.
Oh, canonical divisor is not necessarily a principal divisor.
Means non-zero now.
It's the divisor of a meromorphic, non-zero meromorphic one form. Yeah. It's the any canonical divisor, i.e. the divisor of a non-zero. I mean, I always assume non-zero of a non-zero meromorphic one form. Of course, meromorphic one form on X. G is the genus of X. And degree of D you already know. So we have already defined all terms in the statement. And for example, one thing that's not clear is that why this space is finite dimensional. Because this is just a space of some meromorphic functions with this condition. Remember, what does this divisor of F plus D means? This means that basically at any point, the valuation of the divisor is non-negative, which means that order of F at P for all P plus D of P bigger than or equal to 0 for all P belonging to X. So then this goes in the opposite way. So if D of P is negative, then it means that F has to be holomorphic at that point with a 0 of a certain order, which is should be bigger than or equal to negative d of p, the order of the zero. Okay? So if d is negative at the point, but if d is positive at the point, the condition allows to have poles. Because it goes to the other side, it becomes negative only. So it means that it can have poles, but not very bad poles. I mean, the poles has to be bigger. The order has to be bigger than negative d of p. Okay, so this is, as I said, this is a kind of a strange way, because if you look at it, this is a strange way of defining a class of meromorphic functions. I mean, and it's also very non-trivial to show, we will show it today, that this is finite dimensional. But as I said, actually, when we learn that divisors are more or less into one-to-one correspondence with line bundles, then what happens is that this is actually a space of holomorphic sections of that line bundle. And then finiteness is a special case of finiteness of solutions of elliptic PDEs. So there's an analysis background to that if you want, but we'll follow a completely algebraic approach to this. Okay, I think I don't want to say anything right now about this. Okay, so but the question is how to prove it. Okay, so we will start. So, okay, it's a good idea to look at some examples first. Okay, so one thing, okay, first of all, one lemma first. If D is a negative divisor, this degree is negative, degree of D is less than 0, then L of D is actually 0, there's nothing there, and L of D is equal to 0 as a result. So for negative divisors, there are no elements here except for the 0 function. If we have a negative divisor. Okay, so why is that so? I mean, the proof is just straightforward. The proof. So the condition f belongs to L of D means that divisor of f plus D must be bigger than or equal to 0. But here it just means that divisor of f is bigger than or equal to negative D. But this is a strictly positive divisor, because no. Okay, so no, I should not do. Okay, so I'm going to take. Okay, so that's okay. Now what we do is the following. I just apply a degree to this degree of divisor of f plus D is bigger than or equal to 0. So then we get that degree of divisor of f plus degree of D is bigger than or equal to 0. So this means that degree of divisor of f comes out to be bigger than or equal to minus the bigger than or equal to negative degree of D, right? Negative degree of D. But D has negative degree, so negative degree is positive. So this is a strictly positive number. And is that possible? So if there is an f, which is non-zero, in L of D, its degree has to be, degree of divisor of f has to be strictly positive. Is that possible?
Is it not always 0?
the degree of divisor of any meromorphic function, we proved, actually we gave two proofs, that is 0. So, but this is 0. So this cannot be positive. So this is a contradiction, and that's what gives us the proof. So, but that's something very useful to have in mind. If you have a divisor whose degree is negative, there are no elements in L of D. So L of that divisor is 0. So line bundles with negative degree, they don't carry any non-trivial holomorphic sections. Okay, so now let us look at an example. It's good to work with some examples. Unfortunately, the only example we can work out now is, again, our old friend looking at C hat. So let's pick a divisor on C hat. What do you pick? I'm going to pick D equal to 0 to 1 times 0. Let's pick a divisor which is located at 0, right? So let D be equal to 1 times 0. That's our divisor. And we want to check Riemann-Roch against this. So what do you choose for K? What would be, so this is a canonical divisor. What is K now? What is a possible choice for K?
DZ.
Huh?
DZ.
It cannot be dz because K is a divisor. So its expression is different mathematically.
Yes.
So what's it called? Syntax is wrong. The semantic, I don't care. The syntax is wrong. You know what I mean? Okay, so what would be the thing now? You have to choose a meromorphic one form on C hat and take its divisor, and that would be your divisor. So this would be something like divisor of omega. Let's take the simplest meromorphic one form that we can imagine on C hat, which was
DZ.
DZ. Exactly. Now that's what you meant. Okay, so to be fair, that's what you meant. Okay, very good. That's DZ. Okay, so what is this divisor? So this guy has only one pole at infinity and no 0, and in fact, K is equal to -2 times infinity. So now we want to check that L of 1 times 0 minus L of K, -2 times infinity minus 1 times 0 is equal to degree of D. Well, what is D? Degree of this guy. What is degree of that divisor? What is degree of D? Don't doubt yourself. You're right.
1.
1, yes. You just add all these things. This is 1 minus so it's the degree of D minus genus. What is genus of this guy? 0, and then plus 1, right? Remember, this was the formula, L of D minus L of K minus D is equal to degree of D minus G plus 1. This was the formula. So this gave us this. So now the question is this correct? Of course, by Riemann-Roch, we know that this is correct. But the point is now we want to compute all these things explicitly and verify the Riemann-Roch in this case, in this simple case. Okay, so L of 1 times 0 is equal to dimension of L of 1 times 0. And this is dimension of the following space of meromorphic functions on C hat. So the set of Rf from C hat to C meromorphic such that divisor of F plus 1 times 0 is bigger than or equal to 0, right? So what does this mean? It means that divisor of f, there's only one condition because this guy is non-zero only at zero, the divisor, right? So there's only one condition which means that the order of f, so let me put it this way. This is if I'm only order of f at zero plus one has to be equal to zero, right? Yes.
Why is the order of k equal to 1 in this?
Order of k, did I write 1? Did I write order of k equal to 1? Did I compute order of k at all? I mean, order of k, you cannot compute, you didn't define order for divisors. Again, it's a question of syntax.
I think you meant the. Oh, is it, sorry, the degree, yeah, sorry.
Oh, the degree.
Yeah, sorry, yeah.
Oh, the degree, oh yeah, the degree is, what is the degree of this divisor?
It's, did you say it was 1? I think it's 0, isn't it?
Is it -2?
What is the degree of this divisor?
-2.
It's -2. It's just you're adding all the coefficients. Infinity is just a point. It's not. It's just a point. It's -2. That was a good point. Yeah, it's -2. Yeah, degree of d, which is -2. Why did I put 1? I don't know why I put 1.
Is that the degree of d?
Hmm?
Is that the degree of d?
Oh, this is degree of d. Yes. So then what are you complaining about?
If you mind how you like construct the divisor associated to 1. Why it's
Divisor?
-2?
Huh?
Why it's -2? Why the coefficient is -2?
Oh, okay. So let me. Okay, so I'll answer. But are you happy now?
Yeah.
Completely?
Yeah.
Okay, good. Now, so this I explained in my last lecture. So what is this divisor of 1/4? See, divisor of omega, in this case, so let me compute it. Well, I mean, I have to write this near at infinity, right? So, okay, so this is the question, I guess. That was your question. So just use the coordinate w equal to 1/z at infinity. Because we don't know what is the form of this differential at infinity. We just bring it near 0 and then study it near 0. Okay, and it doesn't matter. So then dz is equal to d of 1/w. This is negative dw over w squared. So it is it has order -2, but is not at 0 at infinity because we just use coordinates. Is not. So that's this one. Okay. So are you okay with this now that we want to verify this? Okay. So right hand side turns out to be 2, and this has to be okay. Now what is this space? The set of all meromorphic functions on C hat such that order of f at 0 plus 1 has to be bigger than or equal to 0. What are these functions now? How many functions are there? So this is L of, this is, so in other words, what this condition tells you.
That's all holomorphic functions and all functions with poles of degree -1.
Right. So basically, this means that at all other points, so let me write it like this. I should write it for all p different from 0, right? For if p is not 0, this guy is 0, this divisor is 0 at non-zero points, and then it has to be bigger than or equal to 0, which means that the order has to be bigger than or equal to 0. So there are both conditions. So now what does these two conditions together conspire to tell you? Okay, so first of all, what are meromorphic functions on C hat? These are just rational functions, yes. So here, what we are looking at, if we are looking at a rational function that whose order at 0 is bigger than or equal to -1, and then there are no other poles or zeros, okay? So what are they? So is 1 over z, for example, acceptable?
Yes.
Any polynomial over there?
Any polynomial over z? Ooh, that's dangerous.
Any polynomial not divisible by 0 over there?
That's too big. No. This means that, look, I mean, write the Laurent expansion of this guy around 0, okay? If you write Laurent expansion around 0, you're going to get a over z plus b plus c plus dz plus ez squared. Okay, I'm writing like a high school student here, so that's okay. Just and then go on, right? Oh, why did I write this? No, okay. Okay, so let me write it in a good way. I just write a minus 1 z plus a 0 plus a 1 z plus a 2 z2. So this is for z different from 0 and infinity. You know that your function f is of this form. So you know that you should not go below 1 over z, because if you go below 1 over z, it means that the order at that point is not bigger than equal to -1. The order, for example, is minus 2 and wait. Yeah. We cannot. This is going to decrease, so it's not going to be. Okay, so this. But now I claim that it cannot have any z factors either. Why? Your function cannot have any z factors.
Because roots,
Huh?
because roots then, so that you have non-zero problems at other points.
The roots is a bit delicate because this is an infinite degree, and we don't know if because if you just have a rational function, you expand it, you get something infinite expansion. However, we know that if there is something like z or z squared at infinity, well, what's going to happen at infinity? Has a pole. At infinity is going to develop a pole, but we don't have a pole according to condition doesn't allow a pole. So it means that only these two terms are allowed. Okay. So we have to be very careful now, go slowly. So this means that we are deciding that dimension of this capital L, or in fact, we are saying that L of D is 2. Okay. So let me write it here. Okay, so L of D in this case is equal to 2. So now the next question is, what is L of k minus d, which is -2 infinity and -1 times 0, right? So what is that? So we have to verify, we have to find that thing as well. So let me now erase this. Okay. Where is that? So F belongs to L of -2 times infinity, -1 times 0, if and only if order of F at infinity, and then I've got -2, so it goes to the other side. Okay, so let me put it like this, plus order of -2 infinity. Okay, there's no order here, so okay, so let me put it like this, -2 must be bigger than or equal to 0 if and only if order of F at infinity is bigger than or equal to 2. I guess this is correct. And there's another condition, which means order of F at 0 has to be 1 at least, right? Has to be 1. And then order of F at t just has to be bigger than or equal to 0 for all p different from infinity and 1, infinity and 0. You're happy with this? Okay, then. Okay, so it should be like that. So what are these now? So what is this condition now? Order of f at infinity. So it means that f at infinity. What's that?
The last condition.
Why this is the case? Oh, because the condition is that, I mean, f belongs to, in general, L of d, if and only if order of f at t plus d at p bigger than or equal to 0. Now, if p is not one of these 2 points, infinity or 0, the thing at that point is 0. So it gives us the 0 condition.
Oh.
Okay, so this is explicit. Okay, now let's look at this. What is this? So we have 3 conditions for our function. So again, it's a good idea to write it in terms of Laurent expansion around 0. Laurent expansion around 0. So what do we get? So if you just write it, you just write f of z equal to sigma an zn, and from minus infinity so to infinity. But I mean, we know that at minus infinity, I mean, it really doesn't go all the way up to minus infinity. It stops at some finite negative, possibly negative number, right? That's okay. All right. So now, what this condition tells us? Order of f at 0 is to be bigger than or equal to 1. What does that say? It means that there cannot be any negative terms, and there cannot be constant term either. So it has to start with degree 1 at least. So you have to, okay, so it means that f of z has to be of the form a1z plus a2z2, so on. Good. Okay, now then what? Now we have got order of f. So this condition order of f at infinity bigger than or equal to yeah, but at 2. What does this mean? Order of f at infinity bigger than or equal to 2.
A2 is not 0.
So it means that it has to have at infinity, the guy has to have a 0 of order at least 2. You must have a 0 of order at least 2 at infinity, right? So is that possible with that?
If A1 and A2 are 0. If A1 and A2 are 0.
If A1 and A2 are 0, you're going to get the order at 0? Really?
It's not possible.
It's not possible? Do you think so? This guy doesn't have a 0 at infinity? No, it's not. It's actually infinite at infinity, this guy.
It has a pole.
It has a pole. Okay, not possible. Okay. So it looks like we are saying that actually this second factor that we are subtracting is 0. Okay, so I hope we are okay now. This is 0. L of d, what did you find for L of d over there? Is that 2? Yeah, this is 2. 2 minus 0 is 0, and this is 2. So it varies. So Riemann-Roch were right in this case, at least. This is really the most trivial case, if you can imagine. The most, I mean, the easiest case that you can check by hand. Okay, so this is. Now you can imagine if I give you a general divisor on C hat, and I ask you to verify Riemann-Roch in that case, it's going to be a very kind of lengthy actually exercise, because you really have to be very, very careful about orders and this thing. The thing is going to be correct, of course, but verifying it by hand is going to be, that's why I'm going to give this to you as an exercise very soon. So it's coming your way. Be well. So exercise is going to be the following thing. Verify Riemann-Roch by hand. Whatever it means. I don't know. Now for x equal to c hat and any divisor E, which you can write it as sigma ni times pi, I from 1 to n, plus some number in infinity times infinity. Because we have to allow something at infinity as well. So pi different from pj belonging to the finite part of c hat. Which is c. I mean, you have to work with rational functions in a kind of careful way, but you'll do it. Okay. Now, one more comment about Riemann-Roch. So again, we remember the formula is this: L of d minus L of k minus d equal to degree of d minus g plus 1. Actually, I'm going to make two comments. The comment one is that Riemann only proved an inequality, okay? So Riemann's inequality is this. This is what Riemann proved in his paper in 1857, Contributions to the Theory of Abelian Functions. Riemann inequality. He proved the following thing: L of d bigger than or equal to degree of d minus g plus 1. But just how bigger this left-hand side is from right-hand side, whether it is something or not, it was discovered by Roch a few years after Riemann. So Roch, actually, you can try to read Roch's paper that's available. It's German, but you can ask ChatGPT to translate it for you. Happily, it will translate in fraction of a second for you, with all the, even the latex it for you. So if you want, you can get it. It's a wonderful read, but it's not understandable. It's completely. So Roch found the missing term, namely L of k minus d. So this term has to do with differential forms, which was missing in Riemann's thing. So who was Roch? Some people think Roch was Riemann's student. He was not Riemann's student, but he was in Göttingen when Riemann was lecturing on these things, and he already had obtained his PhD somewhere else. But he heard these things from Riemann apparently. But he did this more or less around, more or less same year as Riemann died, or something like that. It's quite close to. So, but anyhow, so this is Riemann-Roch stuff. Now, one thing is that it's quite annoying to have the difference, because what one would love to have is to have this expression for dimension of a space of meromorphic functions that satisfy some conditions, because that's the goal of things. You want to count the dimension of a space of certain types of meromorphic or holomorphic functions that satisfy some condition. So if you could have a formula for L of d itself, that would be fantastic. But it's not possible to have such a formula. And the reason not possible to have such a formula is rather subtle. The reason is that actually this L of d turns out to be kernel of a differential operator between two spaces. And do you think the dimension of the, or do you think the kernel, which is dimension of the kernel, which is called nullity, could ever be a continuous function?
No.
Is nullity a continuous function? So this is a linear algebra. This actually could be a good for those who may write the comp sometime. This could be a good comp question. I have a 4x4 2x2 matrix A, B, C, D. Okay, and I just take the function from say from M2 of R to R that sends A. Actually it goes to Z even. That sends A to kernel of A. Is this a continuous function? Is it, you think? The function that takes a matrix, I mean, 2x2 matrix to its kernel. Is it a continuous function? Why not?
I mean, you can consider zero matrix and just shift a little bit, right?
You can perturb a little bit around this point and then kernel jumps. Kernel jumps. So it's not a continuous function. So if you had a formula which would give you only L of t, which is kernel of some differential operators, infinite dimensional parameter, this would mean that that function has to be continuous, but that's not. So that's the thing. It just, I mean, in the language of vector bundles, it really means that if you have a bundle map, if you take kernel of a bundle, the kernel of bundle is not a bundle. You need some extra conditions. Okay, so anyhow, so these are the comments I wanted to make about the general statement. Now we can actually start going a bit deeper into this now. Okay, so as if over this example. Oh, okay, yeah, right. So I want now to define another space which is related to the second term, which is called omega of D. Yeah, so any questions, by the way? And so this omega of D, of course, D is a divisor, right? The set of all omega. Okay, I'm going to introduce a notation which is I call M1 of X. So this is a space of meromorphic one forms on X, such that divisor of omega minus D is bigger than or equal to 0. Yes. So we change sign now. It's a kind of duality between functions and forms that's responsible for this, but for now, let me just define it like that. Okay, so this is space of meromorphic one forms. On X. So now there is a lemma I want to prove, which is as some components, I believe. The first part says that L of D is equal to 0. Oh, I already proved this, but that's okay. L of D is equal to 0 if degree of D is negative. This already we proved. And omega of D, this is interesting. Omega of D is equal to 0 if degree of D is large enough, bigger than twice genus minus 2. 2. 2 says that dimension of the quotient space L of D plus Q. Okay, so first of all, let me just okay, so maybe I'll just write it like this for every D. And any q belonging to x, L of D, first of all, is inside L of D plus 1 times q. And omega of D.
Is Q a point?
Huh?
Is Q a point?
Q is a point on X, yeah. Just any point you want to take, and then you form this divisor, which is 1 times that point. So it takes value 1 at that point and 0 everywhere else, right? Okay, good. So we have omega of D goes the other way around, contains omega of D plus 1Q. Also, these are the two most important inequalities now. Dimension of L of D plus 1Q, because that's a subspace, right? So if you divide by this, by L of D, it's going to be less than equal to 1. And dimension of omega of D by omega of D plus 1Q is also less than equal to 1. Yes, that's right. And statement 3 is that the third part is that L of D and omega of D are finite dimensional. And this is really amazing. L of D and omega of D are finite dimensional. Complex vector spaces. So at least the statement of Riemann-Roch makes sense. Are finite dimensional. These are finite dimensional spaces. Okay. All right. So let's go one by one to the proof. So this one, already I proved that if L of D, if degree of D is negative, then L of D is 0. This we already proved using degree of divisor equal to 0. Divisor of meromorphic function is equal to 0. Now what about this? So I'm gonna, can I erase this? Is it okay to erase? So I just erase this. And then I'm going to now focus on second part of the first statement. Proof of this. Okay, so let omega belongs to omega of D. So, but now what does this mean? It means that divisor of omega, right? Minus D has to be non-negative, right? Has to be bigger than or equal to 0. Okay? So now I just apply degree to both sides. So then I get, from here, I get that. This is only one direction. It's not the other way around by any means. We get that degree of divisor of omega minus, bigger than or equal to degree of D. But degree of D, we are told, is bigger than 2G minus 2. So this is bigger than 2G minus 2. If there is a meromorphic 1,4, which is in this space, then its degree has to be like that, right? Is that possible? So this is the question. Is this possible?
But the degree of the meromorphic one form is always 0.
Sorry?
It's always 0.
What is always 0?
The degree of the meromorphic one form.
degree of a meromorphic one form, you mean the degree of the divisor of a meromorphic one. Again, syntax. So degree of a divisor of a meromorphic one form, no, not at all. So we have like dz. What was its degree? It was -2 on x, so that's not true. So what is going on? I proved the statement in the last lecture that, so recall I proved, this was a non-trivial statement, I proved that degree of, in fact, of divisor of any meromorphic one form is equal to negative Euler characteristic of the surface, which is 2g minus 2. This is what I proved in the previous lecture, I remember. And the proof was not trivial. It was a kind of judicious use of Riemann-Hurwitz formula and that function. Okay, so this is no, because it clashes with this, because here you have got 2g minus 2. Always, for any omega non-zero, is 2g minus 2 cannot be bigger than 2g minus 2. So you see, it's a bit similar to the degree of divisor of f equal to 0, but here degree of divisor of omega is fixed, is 2g minus 2. It's different. So for that reason, that space is also 0. So let me just, before finishing for now, let me just write these two results that we proved. One of them quite old. Degree, the two results, these are kind of golden results, degree of divisor of f equal to 0, and then the other one was degree of divisor of omega is equal to 2g minus 2, which is equal to negative Euler characteristic of x. This, we gave two proofs for it. This, we had only one proof, but I mentioned that there is a qualitative difference between the two. Do you remember what was the difference between the two proofs that I emphasized in the last lecture? I said that, and you recall, it's in your notes, that this is always true. You don't have to assume anything. But to prove this, I had to assume that there is a non-zero meromorphic function on x, because I used that to pull back this dz from the target back in, and then I had one non-zero meromorphic one form. So from non-zero meromorphic function, I constructed non-zero meromorphic, and then I worked with that, and then. Now, the existence of a non-zero meromorphic function on x is not a trivial matter for abstract Riemann surfaces. That's Riemann's existence theorem. But for algebraic Riemann surfaces, which are like plane curves or projective curves, this is not a problem. You have all the coordinate functions are meromorphic. So that's why there is a difference between the two statements, but they are more or less on the same level. Both of them say something is constant. In this case, constant is 0. In this case, constant is 2g minus 2. Okay, so then I can start in the next lecture the rest of the proof. We have to go slowly, otherwise there's no point of going too fast. Yeah. Okay.